Myself, Dr. Anindya Sundar. I am working as an assistant professor in Department of Electronics and Communication Engineering in Swami Vivekananda Institute of Science and Technology, Dakshin Govindapur, Kolkata. This is basically a special lecture video, okay, on the topic of root locus, discussing about some important problems. Okay, so in this lecture video, I am uploading some total 5 problems with their solutions on the topic root locus, okay, of the subject control system and instrumentation. So I have uploaded the concept of root locus, okay, the locus or movement of poles, okay, in S plane if as we vary k value from 0 to infinity. Okay, from that we can predict the nature of the system, that is the stability and the output response. And there is another point, that is how we can find out that any point, okay, if we have given a point, whether that point lies on root locus or not, that we can find out using angle condition and value of gain parameter k, that we can find out using magnitude condition. Okay, and I already discussed about the root locus construction rules. Okay, and I have solved some problems in this particular lecture as requested by my students. I am uploading this particular lecture video discussing about some critical problem on root locus. Okay, now this is the first problem where open loop transfer function of a unity feedback control system is given. Okay, we have to plot the root locus and predict the stability. Now from this particular transfer function, what we can see, we have two poles at s equal to -2 and -3, and this is a quadratic equation, so we have the zeros at, using the Shidhar-Acharya formula we can find out -1 plus minus j1. Okay, so in that case what you can see, that number of p, we don't have any asymptotes. Okay, though there should not be any location of centroid, because p minus z equal to 0 here. Okay, number of pole is 2, number of 0 is also 2. Now we can plot that in S plane. This is the location of 0, these two are location of pole. Now we have to find out real axis segment. Okay, mark the root locus, mark the root loci that exist on real axis. So if you look here, what we can see on real axis, there is no pole and 0, and between these two area, what we can see, only one pole. Okay, real pole you have to consider, don't have to look for these complex zeros, okay, or complex pole. So what we can see, one, so root locus existed, and on this particular point or after this pole we can see two poles, there is no root locus path. So this is the two point. Okay, this is the root locus path that existed. And what we have two poles, so there must be a breakaway point, and that must go and it should merge with these two zero. Okay, so you have to find out this breakaway point and you have to find out this angle of arrival. Okay, you have to find this angle of arrival, that we have to find out. Now, so what is the first point? You have to find out the breakaway point. So breakaway point means 1 plus GSH is equal to 0, characteristic equation you have to form, and you have to find out k equal to what. Okay, then you have to perform decay by ds equal to 0. Okay, so if you solve it, decay ds equal to 0, and if you solve it, we will get this equation. From that we can find out the value of s. Okay, we got two values of s. Okay, now which one is the valid breakaway point, that we can find out looking into this root locus, that is minus 0.28. Minus 0.28, we don't have root locus path existed. Okay, so that should not be the valid breakaway point. Minus 2.38, that is here. Okay, somewhere here, so this should be the valid breakaway point. Now we can cross check that if you put this value into this k equation, okay, and we have to check whether k value is positive or not. If we put this s equal to minus 2.38 in this equation, k equal to this equation, we will get k value is 0.08 positive value, so it is a valid breakaway point. If we put this minus 0.28, you can find out k becomes negative. That is not a valid breakaway point. Now what you have to find out, angle of arrival. Okay, so with respect to this 0, if you think the angle theta z equal to what, 180 degree, the formula is 180 degree minus theta p summation. Okay, so summation of theta p, okay, then plus summation of theta z. Angle of pole should be negative, angle of 0 should be positive. Okay, so 180 degree minus, so we can draw a line here. So this is the angle from this pole, draw a line here, this is the angle. Okay, and we can draw another line from this 0, this is the angle. So from this pole, what is the angle? Tan inverse 1 by 1. Okay, 180 degree minus tan inverse 1 by 1, and this angle is tan inverse 1 by 2. Difference is 2 now. Okay, 1 by 2 plus this is 90 degree because this is a 0. These two poles show negative sign, this is 0 show positive sign. So if you calculate, this is 198.5. So from this it will go like this way. Okay, that is the plot. That plot we can observe in the this diagram, okay, that I have taken from MATLAB. Okay, now here we can see this is the point, that is the breakaway point, minus 2.39, that we can find out, minus 2.38. Okay, and the gain is 0.08, and we can see here also gain is 0.08, right? So this is the plot. This pole breaks away and merge with this 0, this pole breaks away and merge with this 0. So there is no asymptote, p minus z equal to 0, so there is no concept of centroid, and this is not, there is no asymptote means it is not going to intersect with imaginary axis, so this system will be absolutely stable system. Okay, and when these two poles, okay, are here at k equal to 0, it will be over damped case. If it reaches to this breakaway point, become critical damped system. As k increases, it goes into complex plane, response should be under damped. So this is the prediction of the system. Now let us solve another problem. This is the transfer function. Okay, now from this we have to find out pole and zeros. So we can see that poles are at minus 1 and plus minus 2. From this we can get minus 1, and a square minus 4 equal to 0. If we put that, then s square equal to 4. Okay, and from that we can find out s equal to plus minus root of 4, which is 2. Okay, and 0 is at plus 1. So here if you look how many number of asymptotes should be there, we have 3 poles, okay, and 1 finite 0 and 3 finite 0 pole. So we have 2, 3 minus 1 2, so we must have 2 number of asymptote. From that we have to find out the centroid, okay, and angle of asymptote. Okay, angle of asymptote we have to find out. So these are the 2 points we have to do. Now before that, let me plot the pole 0 map in the S plane. What you can see, we have a plus 2 pole, minus 2 pole, minus 1 pole, and 0 at plus 1. So if you look, we have to find out the real axis segment. On the right hand side, we don't have any pole and 0. Okay, at this point on this area, what we can see, 1 pole, odd number, so root locus path existed and direction should be pole to 0. Okay, so this pole merge with this 0 as k goes from 0 to infinity. Now if we look at this point on right hand side in this particular area, what we can see, we have 2 pole and 0. Even number, so root locus path does not exist. Now if you look here and between these two area, on the right hand side we can see we have 3 poles and 0, so root locus path existed. After this pole, if you look on right hand side, we have 4 pole and 0. even number, so there is no root locus path on real axis. Okay. Now what we can see, these pole merge with this 0, and these two pole should break away from any point, and it should go along the asymptote. Okay. So we have to find out centroid and angle of asymptote. For that, centroid formula, that is finite value of poles minus finite value of zeros. The poles are at +2, -2, -1. Minus of finite value of 0 is 1. P minus z, 3 minus 1, so you get value as -1. So centroid is at this -1 point. Now angle, P minus Q value, angle formula is 180 degree into 2Q plus 1 divided by P minus Z. Q value should be from 0 to P minus Z minus 1, which is equal to here 2 minus 1, that is 1. So Q value should be here 0 and 1. Okay. So if you put Q equal to 0, it will be 90 degree. Okay. And Q equal to 1, it will be 270. So from real axis 90 degree, and from real axis 270 degree. So these two pole should break away from one point, and it should go along this centroid, along this asymptote. Okay, along this asymptote to infinity 0. Okay, one pole merge with one finite 0, other two pole merge with should have, I mean, these two pole should merge with the zeros which is at infinity, and that should go along this line, centroid, asymptote line. Okay. Now what you have to do, you have to find out breakaway point. Then your problem will be over. So breakaway point means characteristic equation you have to form, 1 plus GSH is equal to 0. Okay. We have to find out what is the equation of K. Fine. Then perform dk by ds, put equal to 0. So if you perform dk by ds, you will get this equation. From that, you have to find out the value of s. Now that a third order equation. So to find out roots of that, you can solve by your own, or you can use scientific calculator to find out the roots. Okay. So s value is this one, minus 1.48, and a complex number. Okay. Now if we put this s value into this k equation, okay, we can see, or we can observe that k value becomes 0.35. So that is the valid breakaway point. Okay. And we can see minus 1.48, this is between 1 and 2, minus 1 and minus 2 points. So that should be the valid breakaway point. And if we put this complex number, okay, into this k equation, you will find k value becomes a complex one. So k value should be positive. After putting the s value, k value should be positive, not complex number, not negative, to get the valid breakaway point. Okay. So this is the problem. So what we can have here, that pole is at minus 1.49, I mean that breakaway point that we can see here, minus 1.48, and gain is 0.35, and k gain is 0.35. Okay. And your centroid is around minus 1. So this pole merge with this 0, this pole comes here, breaks away, and it should go along the asymptote 90 degree line. Okay. Centroid at minus 1, okay, to infinity 0. This pole comes here, break away, and it should go along the asymptote which is at 270 degree line, starting from minus 1 point, centroid. Okay. So this is the simple plot. Now what is the stability of the system? As we can see, we have a pole, this root locus path not entering into the right half plane, then also the system is unstable. Okay. This system is always unstable because we have a pole at right half plane of S plane. Okay. So this is the problem 2. Now let me discuss about problem 3. What we have, this is the transfer function. So first point, we have to find out location of pole and 0. Then we have to plot on S in the S plane. Okay. So we have 0 at S equal to 0 and pole at minus 1, x square plus 1. That means x square equal to minus 1. If you take root of that, minus 1 root over of that, that is equal to j. So s equal to plus minus j1. That is the root. Okay. So what we have, if you plot that, we have a 0. Okay. At s equal to 0, pole at s equal to 1, minus 1, and we have complex pole plus j1 minus j1. Okay. Now we have to find out the real axis segment. Okay, so if we look here in this area, we don't have any pole and zero, so root locus path does not exist. If we check from this area to this, okay, in this particular area, what we can see on the right hand side, we have 1 0. Okay, so root locus path existed. We have to look for the real pole and zero. Don't have to consider this complex pole. Now if you look after this pole on the right hand side, what you can see, we have two poles and zero, so no root locus path existed. So this pole merge with this zero. Okay, what will happen to these two poles? Okay, these two poles should go along the asymptote. Okay, in the direction of asymptote, it should go to merge with infinity zero. But now we have to find out that how many asymptotes are there. So here number of asymptotes should be 2, because we have 3 pole 1 0, 3 minus 1 2. So we can now find out the centroid and angle of asymptote. So now centroid, real part of finite value of pole. So minus 1 and plus minus j, so that will be 0. Okay, and 0 at s equal to 0. Okay, so it will be minus 0.25. So at minus 0.5 we have this 9, and p equal to z, p minus z equal to 2. Okay, so we have q should be 0 and 1. Okay, and let me just change this to degree. Okay, so now what we can see here, what we can observe here, that q0 1, so if you put q equal to 0, q equal to 1, we will get 90-degree angle and 270-degree angle. Okay, so these two poles should go along this uh, centroid, I mean along this asymptote line, to merge with the infinity zero. Now we have to find out its uh, angle of departure. Okay, now you have to find out its angle of departure. At what angle it should depart. Okay, at what angle it should depart, that you have to find out. Okay, so that is the point. So we have to find out angle of departure of this pole. Then what we can see, if you take a from this pole, if you consider, that will be theta p equal to 180 degree minus, from this 0, this angle is plus 90 degree. Okay, 0 plus 90 degree. From this pole, if you connect, the angle should be minus 90 degree. Okay, and from this, with respect to real axis, this angle is phi pole 1. Okay, so plus minus, it will be cancel out. Okay, 180 degree minus this angle is nothing but tan inverse 1 by 1. Okay, so we got 135 degree. So at 135 degree angle, it should go along this. Okay, at 135 degree angle, it should depart, and then it should go to approach to the infinity zero along the asymptote line. So this is the plot here. Okay, your asymptote line is around zero point 0.5. Okay, 90 degree to 70 degree, and this pole merge with this zero, and these two pole goes along this asymptote line to infinity zero at depart at 135 degree angle. Okay, this is the problem 3. Now let us solve another problem. This is the one of the most interesting problem. Okay, we have this transfer function, so we have to find out number of poles location, s equal to 0 minus 2. Okay, now quadratic equation, so we can find out minus 1 plus minus j2. Here we have 4 pole and we don't have any finite zero, so number of asymptotes should be 4. Okay, so we require to find out the centroid and angle of asymptote, that we have to find out. Now we can plot the pole location 0 minus 2, and we have two complex pole. Okay, if you look for the real axis segment root locus path, what you can see here, we don't have any pole 0, so root locus path does not exist. Between this area, we can see we have only one pole, root locus path existed, real pole, and after that, if you look, two poles are there, so there is no root locus path. So this is the real axis segment. Now we have to find out how this pole breaks away okay, and it should go along the asymptote line to infinity 0. Okay, now what you have to do, you have to find out centroid and angle of asymptote. Okay, if you want to plot that, so centroid means, what is the formula? 0 minus 2 minus 1 minus 1, that is the location, real part of pole. Okay, 0 is 0, so it will be minus 1. So minus 1 is the point where we have the asymptote. Angle we have to find out. Now to find out the angle, we have to use the formula, that is 180 degree into 2 cube plus 1 divided by p minus z. Okay, here p minus z is equal to 4, and q value should be equal to what? 4 minus 1, okay, that is 3, 0 to 3. If you put k equal to 0, 45 degree, 135, 225, 315. So these are the angle that we are getting. Okay, that we are getting here. So we can draw this line. So one pole should go along this way, another pole should go along this way, this pole should go along this way, okay, another pole should go along. So these four pole should approach to the infinity 0 with along this asymptotic line. Okay, asymptote line. Now what happens? What should be the breakaway point? Okay, from which point those poles should break away and it should approach to infinity 0. So we have to find out breakaway point. Then we have to find out that angle of departure of these two poles, and we require to find out intersection point with imaginary axis. All the point we have to find out. Okay. Now let us concentrate on the point breakaway point. Okay. Because we have only four poles, so there must be breakaway point. So breakaway point means characteristic equation 1 plus gs h is equal to 0, unity feedback control system, so h equal to 1. So you can find out equation of k. Now dk by ds we have to perform, make equal to 0. So this is the equation that we got. From that, if you solve, you can find the root of s, roots of the s, it is minus 1 and complex number. Now if you put s value, okay, in this particular k equation, minus 1 is equal to minus 1, we can find out k value equal to 4, positive value, so that should be a valid breakaway point. Then if we put complex number minus 1 plus j 1.22, if we put that into this equation, we can find out k value is 6.25, which is also positive value, so that complex number should be the valid breakaway point. Okay, if we put minus 1 minus j122, okay, then also you can find that is also valid breakaway point because k value is positive 6.25. So here in this particular problem we have three breakaway point. Okay, three breakaway point, that is minus 1 is one breakaway point, minus 1 plus 1 point something, minus 1 point something. So we have two breakaway point. Okay, sorry, total three breakaway point, one in real, two complex. Okay, so the plot is little bit complicated. Okay, not simple one. So one pole comes here, that should go along this way, another pole should go along this way, and this pole should depart and it should go like this way. Okay, this pole should come here, okay, and it should go like this way. Okay, this pole should come here and it should go like this way, and these two poles should come here, it can go like this way, this pole comes here, goes like this way. That should be the plot. Okay, and which pole is going, that we have to find out from the MATLAB plot. Now the main aim is what we have to find out. We have to find out the angle of departure. Say with respect to this, we have to find out. So we have to connect this one to this pole and this pole. So this is the angle 90 degree. So 180 degree minus 5p1. So this is the angle 5p1. This is the angle 5p2, and this is plus minus 90 degree. Okay, this is minus 90 degree. We can write directly because this is perpendicular. So this angle, this 5p1, that angle should be what? This total angle is 180 degree minus this angle from this right angle triangle. Okay. So 180 degree minus 2 by 1. 180 degree minus 2 by 1. And this angle we can find from this right angle triangle. Okay. That is tan inverse 2 by 1. Okay. Now you can calculate, we can see theta p phi p equal to minus 190 degree, sorry, minus 90 degree. That means it should depart vertically down. This should depart vertically up. Okay. Now we have to find out the break intersection point with imaginary axis, because these two asymptotes intersect with the imaginary axis. So your root locus should intersect with the imaginary axis. So how we can plot that? We have to form the characteristic equation. Okay, find out the characteristic equation. We have to put s equal to j omega in that equation and separate the real part and imaginary part. Okay, from imaginary part we can find out the value of omega. Okay, omega, put omega value in this real part. Okay, and we can find out value of k. So that is the problem. Now we can solve it, I mean show the diagram. So what we are getting, this pole should come here. Okay, breaks away, then from this point breaks away, and then it goes to infinity zero. Okay, this point, this pole comes here, breaks away, comes here, breaks away, and it should go like this way. This pole comes here, breaks away, and goes like this way, and this pole also comes here, breaks away, and goes like this along this asymptote line. So this is the plot. So we can see three breakaway point. Okay, and we can see the value. When it is minus 1, gain is 4. Okay, when minus 1 plus minus j 1.22, gain is 6.25. That we can find out from our calculation. Okay, minus 1, k equal to 4, those two complex number. Okay, values are 6.25 gain value. Okay, then we can observe omega equal to 1.58, k is 16.23. That we can see here. This is the intersection point. Okay, I have taken only the value from this point, so we can see gain 16.3, and the pole value is around 1.58. Okay, this is little bit positive, but I cannot keep that mouse in that particular point, but we are getting a close value. Okay, that is 1.58. Okay, that we can see 1.58, and gain is 16.23. It is showing 16.3. Okay, so this is the plot. So this pole comes here, breaks away, goes to here, again breaks away, goes along this asymptote line. Okay, this pole comes here, breaks away, goes along this line. This pole comes here, breaks away, again breaks away from this point, goes along this line, asymptote line, and this pole comes here, breaks away, and goes along the asymptote line. We have this four asymptote line that we have seen already. Okay, so these are the four asymptote line. 1, 2, 3, 4, and angle we already know. So this is one of the most interesting problem. We can see here we have three breakaway point. Okay, we have seen two breakaway point in previous problems. Okay, you can find out that in root locus problem lecture video, and here I showed that we have three breakaway point, one real, two complex. Okay, so this is another most important point. Now let us solve another problem, problem number 5. Here also we have the same type of transfer function. Okay, we have 0 pole at 0 minus 4, and we have complex pole minus 2 plus minus j1. So we can plot that. Okay, in S plane. So 0 minus 4 minus 2 plus minus j1. Okay, now previous problem, like we can have a 3 breakaway point and it can go like this way, but this problem we have to solve it, and we have to find out that where should be the breakaway point and how the poles are moving. Okay, so now we have to concentrate on, we have only 4 finite poles, so all the 4 should approach to 0 infinity. Okay, along the asymptote. So you have to find out number of asymptote p minus j, that is equal to 4. We have to plot the real axis segment. Okay, that is between these two we have the real axis segment. Okay, on this right hand side we have one pole. From here we have two poles, so there is no root locus path. Now you have to find out centroid. So 0, 4 minus 2 minus 2. Okay, so it will be minus 2. So centroid at minus 2. Okay, and angle of asymptote we have to find out. That is what formula, you know, that is 180 degree into 2q plus 1 divided by p minus z, and for when p minus z equal to 4, so range should be 0 to 3. 4 minus 0 minus 1 3. Okay, so 0 to 3 should be the range. If we put q equal to 0 1 2 3, we will get these four angle. Okay, so these are the angle that we can observe here. Okay, so these four pole should approach to infinity 0 along this asymptote line, but how they are breaks away, how they break away, and from which point, that we have to find out. Okay, so before that we can find out the departure angle. Because we have this complex pole, what should be the departure angle of the pole? Let us find out that, then we can find out breakaway point. So if you consider with respect to this pole, what you can see, this angle is minus 90 degree. Then we have to find out this angle. Okay, and what is this angle? Okay, so this 180 degree minus 5p1 minus 5p2 minus 90 degree, that we can write directly this one. Now this angle is nothing but 180 degree minus this angle, which is the, this is the right angle triangle. So tan inverse 1 by 2. Okay, 180 degree minus tan inverse 1 by 2. Then from this right angle triangle we can find out what is the angle, that is tan inverse 1 by 2. Okay, then you can calculate, you can find theta p equal to minus 90 degree. That means these two pole should depart at 90 degree angle. Okay, vertically down, from here vertically up. Right, now you have to find out breakaway point. So we have to write the characteristic equation 1 plus gh equal to 0. Find k equal to what? K equal to k equation. Put tk ds equal to 0. Okay, then we got this equation. From that we can find out the value of s. Now we can see we have three values. All three values are real number. Okay. Now we can put all these three values in this k equation. Okay. Find out the what is the value of k. If s equal to minus 2, k equal to 4, a positive value. So it is a valid breakaway point. When k equal to minus 0.775, it is k equal to 6.25. This is also valid breakaway point. When s equal to minus 3.33, 6.25, so it is also valid breakaway point. Now we can see here that on the real axis, the values are real axis segment from 0 to minus 4. Right? This is the range. And all these breakaway point are lie within that range 0 to minus 4, that range. So these three are basically valid breakaway point. Now we can observe, now we can find out the real axis intersection point with imaginary axis, because these two asymptote intersect with the imaginary axis, so that root locus must intersect with imaginary axis. So what you have to do, you have to form the characteristic equation 1 plus g is equal to 0. From in that equation you have to put s equal to j omega. Okay, separate the imaginary part and real part. From the imaginary part we can find out the value of omega. Put omega value in this real part, make equal to 0, and we can find out k. Okay, so that is the problem. Now we can see the I mean waveform or the graph. So we have this four pole. Okay, so what will happen, we have this point minus 0.775, gain is 6.25, that already we have seen. So this pole comes here, breaks away. Okay, and it should go along this asymptote line. Okay, now this complex pole comes here, breaks away, which point is minus 2, gain is 4, that already we have seen, and comes to that point again, breaks away, and it should go along this asymptote line to infinity 0. This complex pole depart at minus 90 degree angle, comes here, which here breaks away, then breaks away and goes like this way in this asymptote line, along this asymptote line to infinity 0. This pole comes here, okay, breaks away, and it should go along this asymptote line to infinity 0 at a particular angle. That angle of asymptote already we got. So we can see all the gain value and the breakaway point, and we can see all the gain value that we have calculated as same. Okay, so in this problem we can see we have three breakaway point, and all the 3 points are basically real number. In previous problem we observe we have three breakaway point, one real, two complex. So this is how we have to solve this kind of problem. Now we can cross check the imaginary interaction point with imaginary axis. Okay, gain is 48.6 and the value is around 1.61, that we can see here. Okay, 1.58, but this is 46.19. So I am getting little bit higher value because I couldn't get the exact point because this is 0.02. I have to make it 0. So we are getting the result close to that. Okay, so this is the problem. Okay, so I have solved these five problem. Okay, five types of problem, and where we can observe the different type of characteristics. This system is not absolutely stable. It will be stable when k value is less than 46, equal to 46 or 47, marginally stable. Greater than that, it should be unstable. Okay, so this is the most important five problems that can be different type of problems that I have solved and I have uploaded in this particular lecture video. Okay, so you can practice all those problems on your own. Okay, and then you can solve any type of problem on this root locus topic. Okay, so thank you so much.